Welcome to next lesson in the special theory of relativity. Here in special theory of relativity, we will discuss the postulates of relativity and Lorentz transformation. The negative results of Michelson-Morley experiment revealed that velocity of light in vacuum is independent of motion of the observer. It is same in all inertial frames. So we will get the same result if we measure the velocity of light in vacuum. It is independent of the direction of velocity, it is independent of the relative motion between the observer and the light and the source of light, etc. So that was the result obtained from Michelson-Morley experiment. At that time, the classical view or the Newtonian view of space and time were that the space and time are invariant for all observers. It means that the distance measured, for example, the length of a road measured by different observers will be same. And also the duration of the time interval for an event, for example, the time taken by a particle to move from one position to another position will be same for all observers. The time and space are invariant for all observers. This was the view of Newtonian mechanics. And also the velocities and positions were connected by using Galilean transformation of equations. So this was the classical view. But special theory of relativity, it was introduced by Einstein. Einstein dropped the concept of ether completely. And along with that, the accompanied absolute frame of reference. Scientists were believing that there is an ether and there is an accompanied absolute frame of reference with respect to which the velocity of light is c. But the Michelson-Morley experiment revealed that there is no existence of either. There is no such medium called as ether. So Einstein, he was the first scientist to drop the concept of ether completely and the absolute frame of reference. According to Einstein, nothing is absolute. There is no meaning for absolute motion or absolute rest. They are meaningless. So, according to Einstein, both space and time are variable for observers at high speeds. The relativistic effects are more pronounced when the particle is moving at relativistically high speeds, that is, at speeds close to the speed of light. At such high speeds, the space and time are variable. They are not invariant as assumed in the classical view. They are variable for observers at high speeds, so the time duration and the length of an object will be different for different observers if they are moving at relativistically high speeds. And this concept of space and time does not agree with the Newtonian view of space and time. So this is called a special theory of relativity. And the ideas of special theory of relativity are incorporated in two fundamental postulates. They are called postulates of special theory of relativity. The first postulate is the laws of physics have the same form in all inertial reference frames. This is similar to the Galilean law of invariance, provided there is no condition of connected by Galilean law of transformation. It simply says that the laws of physics have the same form in all inertial frames. And this is called, in classical view, in Galilean view, the statement was the laws of physics have the same form in all inertial frames connected by Galilean transformations. But it is not correct because Galilean transformation is found to be not correct in relativistic speeds. So this is the actual form of that principle of invariance. The laws of physics have the same form in all inertial reference frames. And this statement has very important implications. It will be discussed later when we are discussing the Lorentz transformation. Speed of light in vacuum is constant in every inertial system. This is the second postulate. That is, speed of light in vacuum is 3 into 10 raised to 8 meter per second. It is a constant. It does not depend upon the direction of propagation or the relative velocity between the source or observer or the velocity of the source of light. It is independent of that factors. It is a universal constant. The speed of light in vacuum is constant. So these are the two statements called the fundamental postulates of special theory of relativity. Then we are going to discuss the Lorentz transformation. So in relativity, we have found that the classical transformation equation, that is Galilean law of transformation, is not valid. So we have to find a new transformation, and that transformation is called the Lorentz transformation. Now here we will derive the Lorentz transformation. For that, we have two frames of reference. First one is S and the second one is S dash. As usual, the second frame S dash is moving with a constant velocity v along the positive x direction with respect to the frame S. And also, for simplicity, we assume that the two frames are coincident initially at a time t equal to t dash equal to 0. And the space and time coordinates of a particle P as measured with respect to the frame S is represented as x, y, z, t. And the coordinates of the same point with respect to the frame S dash is represented as x dash, y dash, z dash, t dash. So initially the two frames, the two origins O and O dash are coincident. So after a time t, the frame S dash has moved through a distance O dash. Now the position vector of a point P, that point P is such that we assume that there was a source of light at the origin at time t equal to t dash equal to 0. At that time a light wave is emitted from that source. So after a time t, the light wave will have reached a point P. Now with respect to the frame S, the distance travelled by the light wave is OP. And with respect to the frame S dash, the distance travelled is O dash P. Both S and S dash are inertial. So in both frames of reference, the velocity of light will be same. It will be c. We are assuming the vacuum. So that is the result obtained from the Michelson-Morley experiment, or the fundamental postulate of the second postulate of special theory of relativity. That is, the velocity of light will be c in all inertial frames of reference. So in both the S and S dash, the velocity is same. Now we assume that the time taken by the light to travel the distance OP, O to P in the frame S, that will be equal to, time is equal to distance by velocity, that is equal to OP by C. Now OP, O is the origin of the frame of reference S, and P is a point, the coordinate is x, y, z, t. So the distance between OP will be root of x square plus y square plus z square. Therefore we get the time taken as x square plus y square plus z square raised to half by C. It implies that if you take C into this side, it becomes Ct. Taking square on both sides, we get x square plus y square plus z square is equal to c square t square. That is equation number 1. Similarly, with respect to the frame S dash, the light is moving from the point O dash, that is the origin of that frame of reference, to the point P. Now with respect to that frame of reference, the time taken will be t is equal to O dash P by C, because C is same in all inertial frames. So time taken to travel OP dash, not OP dash, it is O dash P. O dash P, that is P is same and this is O dash. The time taken will be O dash P is equal to, in S dash, it will be equal to, we can say it as T dash, because it is the time measured in the S dash frame. It is equal to OP dash by C. That is equal to x dash square plus y dash square plus z dash square raised to half by C. Again, taking the square on both sides, we get x dash square plus y dash square plus z dash square is equal to c square t square. That is some equation number 2. So we see that equation number 1 is the equation connecting the space and time coordinates in frame S, and equation 2 is the same connecting in frame S dash. Now we are checking the validity of Galilean transformation. If we put the Galilean transformation equation, that is x dash is equal to x minus vt, y dash equal to y, z dash is equal to z, t dash is equal to t, in equation 2, we get x dash is x minus vt square plus y square plus z square plus e square t square. So we get x square plus v square t square minus 2x vt plus y square plus z square is equal to c square t square. That is equation number 3. We see that equation 3 is not equal to equation 2. It is not equal to equation 2. It is not equal to equation 1, because we are starting from equation 2 and we are providing x dash is equal to x minus vt. Then we should obtain equation 1, but equation 1 is not obtained because there are two additional terms, v square t square and minus 2x vt. Therefore, Galilean transformation is not valid here, because one coordinate system cannot be transformed into another coordinate system by using Galilean transformation. So Galilean transformation is not valid in relativity. Thus, we have to find a new transformation relation. That new transformation is called a Lorentz transformation. Now, as the velocity of s dash with respect to s is along the positive x direction, we can safely say that y dash and z dash have not changed, because there is no motion along the y or z direction. Therefore, y dash will be equal to y and z dash will be equal to z. Now, by postulate 1 says that the laws of physics have the same form in all inertial reference frames. By this postulate, the transformation relating x and x dash must be linear, because the laws of physics have the same form means if velocity of a particle is uniform in frame s, it should be uniform in frame s dash also. So a uniform velocity should be uniform in both frames. It means that the transformation relation should be linear. If there is a quadratic term, then a linear velocity, a uniform velocity in one frame will not be uniform in the second frame. There will be an acceleration. And it is not possible, because the postulate 1 says that the laws of physics have the same form. It means that a uniform motion will appear as a uniform motion in all inertial frames of reference. So we can say that the transformation relating x and x dash must be linear. Also, the transformation must reduce to Galilean transformation at low speeds. Another important point is the Galilean transformation which is valid at lower speeds. This transformation that we are going to derive Lorentz transformation, that transformation should reduce to Galilean transformation at lower speeds. So the transformation equations can be written as x dash is equal to some constant k into x minus vt, where k is a constant to be found. And it is called a constant because it will be independent of the position and time, that is x, y, z and t. Now s is moving relative to s dash with velocity v dash. S dash is moving along the positive direction. Now from the frame s dash, if we are observing the frame s, now we see that the frame s will be moving with the velocity minus v. It means that the frame s will be moving along the negative x direction. So the relation, the transformation relation connecting x and x dash will be, x will be equal to the same constant k into, that is the equation number 5 is repeated here, x dash plus vt dash. The only difference is x is replaced by x dash and t is replaced by t dash. So this is x dash, it becomes x here, here x, it becomes x dash here, and t becomes t dash here, and minus v becomes plus v here, because now the frame is moving in the negative x direction. And we are using the same constant k because it is as per the postulate 1. Now putting 5 and 6, 5 in equation 6, this 5, that is x dash is equal to k into x minus vt, that is equation number 5. It is put that equation in equation 6, we get x is equal to k into x dash, that is k into x minus vt. k index minus vt plus vt dash, that is plus vt dash. Now that is in equation 6, x dash is replaced by equation 5. Now multiplying we get k square x minus k square vt plus kv t dash, which implies kv t dash is equal to, that is this quantity, it is equal to x is here, x minus k square x plus k square vt, or t dash is equal to, from here we get 1 minus k square into x by kv, dividing this by this quantity, plus k square vt by kv, that becomes kt, or we can write t dash is equal to kt plus 1 minus k square by kv into x. That is some equation number 7, because this is the transformation relation connecting the t dash and t. Now by equation 2, we already have written that x dash square plus y dash square plus z dash square is equal to c square t dash square. Now using the equations for x dash, y dash, z dash and t dash from 4, 5 and 7, we get x dash is k into x minus vt whole square plus y dash is y square, z dash is z square is equal to c square into t dash is this quantity, that is kt plus 1 minus k square by kv into x whole square. So we get, squaring this term, we get k square x square minus 2k square xvt plus k square v square t square plus y square plus z square is equal to c square into, squaring this bracket, k square t square plus 1, that is 2ab, that is 2kt into by kv, k and k gets cancelled, so it will be 2t into 1 minus k square x plus 1 minus k square whole square x square by k square v square, that is square of this term. Now equation, comparing with equation 1, what is equation 1? It is x square plus y square plus z square is equal to c square t square. We have to transform equation 2 into equation 1. So equation 2 is x dash, y dash, z dash squares is equal to c square t dash square. In that equation we have provided the values of x dash, y dash and z dash and t dash, and we obtain another equation. This equation should be equal to the equation 1, because equation 1 is the relation connecting the coordinates of the part of the point P in frame S. So the equation 1 is x square plus y square plus z square is equal to c square t square. So there is no term containing x, but here there is a term containing x. Therefore equating the coefficients of x, we get here the coefficient of x is equal to minus 2k square vt, minus 2k square vt. It should be equal to, here the coefficients of x will be equal to 2, here the coefficients of is equal to 2c square t into 1 minus k square by v, 2c square t into 1 minus k square by v. These two coefficients should be equal because x is equal to 0. So here also x term should be 0. In order to have the 0 x term, the two coefficients should be equal, so that these two terms gets cancelled and we get this equation. Here there is no x term. So equating that coefficients, we get minus 2k square vt is equal to 2c square t into 1 minus k square by v, and cancelling t on both sides and by 2 also, we get k square, and taking this v into this side, k square v square is equal to c square minus k square c square, that is k square into c square minus v square is equal to c square, which implies k square is equal to c square by c square minus v square. Now dividing both sides by, that is numerator and denominator, by c square, we get 1 by 1 minus v square by c square. Therefore k is equal to 1 by root of 1 minus v square by c square. So this is the form of the constant k. It is independent of x, y, z, t, but it depends on v and c. C is a constant, so it depends on v. Now putting the values of k in equation 6 and 7, we get x dash is equal to k into x minus vt. So it becomes 1 by root of 1 minus v square by c square into x minus vt. Y dash is equal to y, z dash is equal to z, and t dash is equal to, it was k into t minus, the expression for t dash was kt plus 1 minus k square by kv into x. Now that 1 minus k square by kv, you can see that 1 minus k square by kv is equal to minus c square by c square by kv, that is equal to, depending on, by solving this one you will get this expression, minus v by c into root of c square minus v square, or minus v by c square into 1 by root of v square minus c square. This is also, actually this is k. So we get that term t dash is equal to k into t minus vx by c square, or t minus vx by c square by root of 1 minus v square by c square. We are putting this term as gamma, that is the 1 by root of 1 minus v square by c square. It is putting as gamma, it is standard notation, and v by c is given as beta, then gamma will be equal to 1 by root of 1 minus beta square. So that equations becomes x dash is equal to gamma in x minus vt, y dash is equal to y, z dash is equal to z, and t dash is equal to gamma into t minus vx by c square. So these are called Lorentz transformations. They connect the coordinates of a point between two inertial frames of reference when the frame s dash is moving with a velocity v with respect to the frame s. And the important point is, if the frame s dash is moving at a very small speed, that is if v is much less than c, then this v by c square will be negligible, and the value of gamma is equal to 1 by root of 1 minus v square by c square. If v is much less than c, then v square by c square will be almost equal to 0. So gamma will be almost equal to 1. So we get x dash is equal to x minus vt in that case, y dash is equal to y, z dash is equal to z, and t dash is equal to t, because gamma is 1 and v by c square will be equal to 0. So in that case we will return to the Galilean transformation. So Galilean transformation is a special case of Lorentz transformation. Lorentz transformation is the correct transformation relation, and it becomes Galilean transformation if the velocities are non-relativistic. Non-relativistic means if the velocities are negligible with respect to the velocity of light, and the relativistic effects are more pronounced only if the system involved is moving with a velocity comparable to the speed of light. So this will be more predominant in the case of atomic world, because in the case of atoms or molecules, the electrons will be moving at a very high speeds, and we can accelerate the particles to high speeds. So at that cases, the relativistic effects are more predominant. So these are called Lorentz transformation equations. So thank you for watching this video.